Last episode, we hit a wall. A plain network drowns when you feed it an image, millions of inputs, billions of weights, and no sense that nearby pixels belong together. The convolutional network fixes all of that with one elegant idea. It's how machines learn to see. An image isn't a flat list, it's a grid of pixels, and structure lives in that grid. A nose is a cluster of nearby pixels. An edge is a sharp change between neighbors. The plane network threw that away by flattening everything. A CNN keeps the grid intact and exploits the one fact that matters most: nearby pixels are related. The core operation is the convolution. Take a tiny grid of weights, a filter maybe 3 by 3, and slide it across the image. At each position, it multiplies its weights against the pixels underneath and sums them, a dot product on a little patch. The filter is a pattern detector scanning everywhere for the thing it's tuned to find. Here is the magic. The same filter is used at every position. Instead of a separate weight for every pixel, a CNN learns one small filter and reuses it across the whole image. That's weight sharing, and it's a massive win. A 3 by 3 filter is just 9 weights, not millions. And because it's the same everywhere, a cat detected in the corner is detected in the center too. As the filter slides across the image, it produces a new grid, a feature map, lighting up wherever its pattern appears. A vertical edge filter creates a map of all the vertical edges. The output isn't pixels anymore, it's a map of where a specific feature was found. The image has been redescribed in terms of patterns. One filter finds one pattern, so a convolutional layer uses many, dozens or hundreds, each tuned to something different, edges at various angles, colors, textures. The layer outputs a whole stack of feature maps, one per filter. Together they form a rich multi-channel description of what's in the image and where. Stack convolutional layers and something powerful happens. A neuron in the first layer sees only a tiny patch, but a neuron in the second layer sees patches of patches, a larger region, deeper still, even larger. This growing window is the receptive field. Deeper neurons see more of the image at once, enabling them to recognize bigger things. And so a visual hierarchy emerges, just like in the MLP, but built for images. Early layers detect edges and simple textures. Middle layers assemble them into parts: an eye, a wheel, a corner. Deep layers combine parts into whole objects: a face, a car. From pixels to meaning, one convolutional layer at a time. Between convolutions, we usually pool, shrink the feature maps by summarizing small neighborhoods, often just keeping the maximum value in each little block. Pooling makes the representation smaller and faster and adds a useful tolerance. The network stops caring about the exact position of a feature, only that it's roughly there. Slightly shift the cat and it's still a cat. Put it together and you get the classic CNN. Alternate convolution and pooling layers to build up features while shrinking the grid. Then, at the very end, flatten what's left and pass it through a few dense MLP layers to make the final decision. Convolution C, the dense head, decides. This design powered a revolution. Lynette read handwritten digits in the 90s. AlexNet shocked the world in 2012, crushing an image contest and igniting the deep learning boom. VGG went deeper. ResNet, with its skip connections, went hundreds of layers deep. Each pushed accuracy further and proved that depth done right wins. And CNNs do more than label an image. Add the right head and the same convolutional backbone can draw boxes around objects, detection, or label every single pixel. Segmentation. The features a CNN learns are so general that they became the foundation of nearly all of computer vision for a decade. So that's the convolutional network. Slide small shared filters across a grid to detect patterns, stack them to build a hierarchy, and pool to stay efficient. It gave machines sight, but images are static. What about data that unfolds over time like language or speech? For that we need memory. Next, recurrent networks. See you there.